In this video we're going to learn about design parameters that we use to describe differential amplifiers, which are an abstraction of the differential circuits we've been looking at. Thus far we've been looking at differential amplifiers like the one pictured here, perhaps with offsets, as I've shown by including extra delta R on the right resistor. However, we can abstract this into a differential amplifier model, just like we abstracted our single-stage amplifiers into single-ended amplifier models. We've already seen a bunch of the small signal parameters that describe this differential amplifier. These are the differential and common mode parameters that we've been finding with our half circuits. And we can add in our voltage offsets from the last video to this amplifier model too. I've chosen to represent the voltage offset of this amplifier as an input referred offset here. And that's a pretty common choice. Though sometimes if you're dealing with big amplifier chains, you'll maybe refer all of the offsets to the output of the chain to see how big the effect of all of them combined is. The input bias current is another parameter used to describe amplifiers. This is the DC bias current that flows from the inputs into the amplifier, so from VIM and VIP into the amp. In our amplifier, this is given by I tail over 2 divided by beta plus 1. Which is we find because I tail over 2 flows in each transistor, and in order for I tail over 2 to be flowing at the emitter, you have I tail over 2 beta plus 1 at the base. Note that if the amplifier were AC coupled, the input bias current would be 0 because it's a DC large signal parameter, and AC coupling only lets AC currents through. If beta is different for QP and QM, then you'll get a slight difference in the input bias current between the two sides, which, rather than changing the input bias parameter, we tend to model as a offset current. So this is a current input referred current offset, just like this is an input referred voltage offset. Finally, though this won't appear on the differential amplifier diagram, both the input and output common modes have maximum and minimum values that they can reach before they start causing some transistors to fall out of the forward active region. We can look at the input common mode of this amplifier for an example of this. I've labeled the tail current source with a voltage V on, which is a current source parameter that specifies how much voltage needs to be across the current source for it to function. So in order to honor this constraint, the VTail node needs to stay at V on or above. And we know that our input common mode is going to be VTail plus VBE on to reach either the VIM or VP side. So the minimum input common mode is V on plus VBE on. We also need to keep QP and QM in saturation, so if we raise the input common mode up high enough, then VTail will squish QP or QM. So that means VTail needs to be below VCC minus VCE sat, and the inputs need to be below VCC minus VCE sat plus VBE on. Okay, because VBE on is bigger than VCE sat, that turns out to be higher than the voltage rail. And so we're actually going to say our maximum input common mode is VCC. So if we take the maximum input common mode, VCC, and we subtract off our minimum common mode, we get our input common mode range. So in summary, differential amplifiers are described by a bunch of parameters. These include the differential and common mode small signal parameters, an offset voltage that is applied to one of the inputs, though if you prefer you can have the offset voltage attached to one output line if you want an output referred offset. An input bias current applied to both of the input lines of the differential amplifier. An input offset current applied to one of the input lines. An input common mode voltage range and an output common mode voltage range.